So I think last time we started with 2's complement. I mentioned that to take the 2's complement of a number, you invert all the bits and you add 1. And that will change the sign of the number. So if it was negative originally, it will become positive. And if it was positive, it'll be negative. 2's complement numbers allow you to do arithmetic on them natively without any special tricks. So for instance, if we have two 4-bit numbers, let's say I want to add, well, first of all, what's the range of a 4-bit number in 2's complement? Well, if it's an unsigned 4-bit number, it would be 0 would be the lower end of the limit. And then whatever v value you want to represent would have to be greater than or equal to 0 and less than or equal to 2 to the n, right, minus 1, where the minus 1 is applied to the 2 to the n, right? So if it's a 4-bit number, 2 to the 4th power is 16, subtract 1 is 15, so we're 0 to 15. If it's 2's complement, the range shifts downward by 2 to the n minus 1, where the minus 1 now is applied to the exponent. So this is the part that's a little confusing, because in this case you got minus 1 being applied to the 2 to the n. When you do 2's complement, you go from negative 2 to the power n minus 1, where the minus 1 in this case, make sure you don't get confused here, the minus 1 is part of the exponent, and then that's less than or equal to the value, which is less than or equal to 2 to the n minus 1 positive, but then now we have to add an extra minus 1 here that is applied to the whole value there. So in this case, if it's a 4-bit number, 4 minus 1 is 3, 2 to the 3rd power is 8, so this would be minus 8, right? This would be minus 8 to 7, right? Guys with me? So why is it that we get more negative numbers than positive numbers? I don't know. That's just how it works. Kind of strange, unexpected. Another way to think of 2's complement is this. If you take the most significant bit, the value of the most significant bit. So what is the significance of the leftmost bit? It's always 2 to the n minus 1, right? Guys with me? So it's a 4-bit number. 8 is the value associated with the leftmost bit. So in a 2's complement, you just make that one bit be a significance of negative 8, right? And then all the other bits that then are just normal, right? You guys with me? So it's kind of a neat way to look at it, I think. So if you have a 4-bit number like that, you could look at that and say, well, I know if it's 4 bits, that means the first bit's 1, so that tells me it's negative. But aside from that, I'm like, well, negative something, I don't know what that is. I can't tell from looking at it. I don't have these things. I don't have the 2's complement thing memorized. I can't just look at that number and tell you what it is. What I used to do was I would just take the 2's complement. So I know it's negative. If I take the 2's complement, it'll make it a positive number. So, invert all the bits. It makes it 4. That's the 1's complement. And then you add 1, 5. So that's negative 5, right? Makes sense? That's what I used to do. But this semester, I was reading the textbook, chapter 1, and they said, well, you don't even need to do that. Just say that's negative 8, right? Because the first bit's negative 8, and that's 3. So just say negative 8 plus 3, 5, negative 5, right? That's easier than having to go through all this stuff. So it's a nice trick. I didn't know about that before I read that. Any questions? Oh, in arithmetic, we'll go through a real quick example there. Arithmetic, let's say I had the aforementioned, I already forgot what the heck it was. 1, 1, 0, 0? No, 1, 0, sorry. 1, 0, 1, 1. My memory is shot. That was what I had, right? That was negative 5, we agreed, right? So say I want to add Well, say I want to add positive 5, right? It should be 0, right? So positive 5, 0, 1, 0, 1, right? 4 plus 1 is 5. So that gives me a 1 plus 1 is 0 with a carry. 1 plus 1 is 0 with a carry. 1 plus 1 is 0 with a carry. 1 plus 1 is 0. Oh, with a carry. Kind of strange, but it's OK, because that carry goes away. It doesn't show up in the result because the result's only big enough to hold 4 bits. So result's 0. So negative 5 plus 5 is 0. There's an extra carry in there, but that's to be expected. In fact, you better get a carry if you ever do these. When you add a negative number, you're expecting that carry there. If you don't get a carry, something bad is happening. Let's say we add negative 5. Sorry, screwed that up again. There we go. 1, 0, 1, 1. Negative 5. Let's say we add it to negative 5, right? Now that would give us negative 10, which would be outside the range, which the bottom end of the range is negative 8, right? So that would be considered an overflow. So does that work out? I guess that would work out. Yeah, that would be OK in that case too. So 0, right? 1, 1 with another carry, right? 1, right? And that would be a 0 with a carry. So that would give me what appears to be 6, right? So, but that actually also had a carry. So in that case, the way I would detect that would be I would have to look at the sign bits of the two numbers I'm adding, as well as the sign bit of the result I get, and that would indicate something's wrong. If you add two negative numbers, you shouldn't be getting a positive number, right, or 0, right? It's impossible, right? So that in that case, yeah, we still got a carry. So again, yeah. So yeah, that one you'd have to look at the sign bits. You guys with me? But the reason why we have an overflow flag or that we care about overflow is because it gives us the wrong result. Okay.
Because of the overflow, that would make it a negative 6 instead, or what
So,
does the overflow do in that case?
The overflow is not as meaningful here, right? If you've got unsigned numbers, if you have two unsigned numbers and you add them, you're not expecting an overflow, right? So if you add two unsigned 4-bit numbers and you get anything greater than 15 as the result, 1, 1, 1, 1, then you're going to have an overflow, and that would mean something's wrong, right? Assuming you're adding. It's different if you subtract two unsigned numbers. But if you add two unsigned numbers, the overflow would mean, or the carryout would mean overflow. Sorry, carryout would mean overflow. If you're adding two signed numbers and you get a carryout, as we did here and we did in the last example, it's not as meaningful.
So, but you were saying because you added two negative numbers, then it should be another negative number, but you have 6. So how would you?
Yeah, it's wrong because of the overflow.
Mm-hmm.
So the presumption here was that the software would have to detect that and do something. The MIPS processor that you guys learned in 212 is one of the few processors that'll actually generate an exception for an overflow. If you use an add instruction. If you use an add U instruction, it won't. But most other processors don't generate an exception, but they do set a flag bit. There's a flag register. And so the software would have to check that flag register, otherwise it would just be it would be a bug. If it doesn't check that and doesn't tell the user, hey, here's an error, then it would be classified as a bug, right? Okay, moving forward. So we talked about that. We talked about that. Some more examples. Sign extension. Sign extension is whenever you want to change the size of the width, the bit width of your number. And so normally, you would think, well, I've got a 4-bit number and I just want to make it an 8-bit number. So I need 4 extra bits. I got to get 4 extra bits. Where do I get them from? Putting zeros in there is one way to do it, except that if the original number was negative, if you put zeros in there, you will have effectively changed the number. You'll change the sign, right? Because you'll end up by putting in, now I'm assuming, of course, you're putting these numbers in the left-hand side, right? So these numbers are right justified. So if you had a number like 3 in 4 bits and I wanted to make it 8 bits, then I would add, I could add, in this case, 4 zeros and I would be fine, because that 3, could be a signed number and just be positive, or it could have been an unsigned number. If, on the other hand, I had a number that was supposed to, if the original value was supposed to be signed, then I know it's negative because that first bit is 1. And so if I want to convert it from 4 bits to 8 bits, I would have to bring in 4 leading 1 bits. I would have to pad it out with 1 bits, right? So basically, you just pad it out with whatever the sign bit is if you want to do a sign extension. You guys with me? So the difference is sign extension, take the sign bit, the first bit, and use that to add more bits, right? To change the width. If it's a 0 extension, then you just always use 0, regardless of the sign bit. Everyone with me? Okay. Anyone know why this is in here, by the way? Why is this topic relevant? In MIPS, in the MIPS and other, I think probably just about every instruction set, you'll have instructions where you can specify an immediate, which is like a constant that's embedded in the instruction. But that constant is inevitably going to be smaller than the bit width of the ALU. You guys remember like the add I instruction from 212? Did you guys cover that? So like and by the way, this is most often used for loop iteration counters, right? So if you have a for loop and you want to say I equals I plus 1 at the end of that for loop, you want to be able to add 1 to a counter, but you don't want to use a register to hold that 1, right? You don't want to use up a register. So you just say add immediate. Well, the immediate value needs to be sign extended because it's usually a 16-bit or a 12-bit, depending on the instruction set, number that's embedded in the instruction. Everyone with me? Make sense? So that's why we're talking about this. It's useful in architectures. It comes up a lot in CPU design. Then we also talked about fixed point last time, and fixed point's kind of neat. It allows you to have a to use the same hardware as you would for integers. When I say hardware, I mean like the instructions. You could use integer instructions, integer ALUs. You can have the number stored in an int variable in your Java code, right? But you might also want to be able to represent fractional numbers, right? So this is like when you took your programming course, they might have told you to use floats whenever you need a fractional number, but floats can be expensive computationally to use. So fixed point is when you just set the decimal point somewhere in the number. So this is an NM number, right? N's the total number of bits. M is the number of fractional bits. So the range of this number, if it is unsigned, the range would start at 2 to the n. Sorry, the range would start at 0 if it's unsigned. Sorry, 0, unsigned, starts at 0. And then it's going to go to 2 to the n minus m. You say, why n minus m? Well, it's n is the total bits. You got to take out the fractional bits. So this is the n minus m is the integral number of bits, the non-fractional bits. But then instead of subtracting 1 as you would if it's not fixed point, remember we did this before, right? We had just minus 1. Instead of subtracting 1, we're going to subtract whatever the value, whatever the significance is of the unit in the last place, which is the rightmost, least significant bit, which is going to be 2 to the minus mth power. Right, so in this case, there's 4 fractional bits. So 2 to the minus m is 2 to the minus 4, which is 1/16. It has a significance of 1/16. So the range would be 0 to 0 to 4. Right? 2 to the second. and then you would subtract from the 4 1/16, right? So it gets you, so basically if you have these all 1s, you'll have 3, right, point, and then whatever, whatever is 1 minus 1/16, so it'll be 3.9 something. You guys with me? Right? If it's a 2's complement number, it's a similar idea. It would start at 2 to the m minus m, and negative minus 1, right? So you got the minus 1 in the exponent, just like we had before, except instead of n minus 1, it's n minus m minus 1, right? That's the lower end of the range. And then v, the value that you want to represent, and then that would go to 2 to the m minus 1 minus 2 to the minus m. Make sense? So what's basically fixed point, the only thing fixed point changes is at the upper end of their range, instead of subtracting 1, you subtract 2 to the minus mth power, which is the significance of the unit in the last place, right? And then, again, unit in the last place being the least significant digit, the rightmost digit, rightmost bit. And then for the upper end of the range, it's just negative 2 to the m minus 1, right? Makes sense? Here I have negative 2 to the n minus 1 divided by 2 to the m, which is equivalent to saying negative 2 to the n minus m minus 1, right? By having that divisor there. Any questions? OK. Logic gates. So I think you guys remember this. Am I right? You remember this from the basic logic gates from 211. The important thing to take away from this is the notion of the truth table. The truth table allows you to define the behavior of a logic gate or any logical logic circuit. You guys with me? This is how you define the behavior. Well, there's one way to do it. The other way to do it would be to have the Boolean equations, right? The Boolean algebra written out symbolically. Now, what's the disadvantage of the truth table is that the truth table is going to grow exponentially, right, with the number of inputs. So these truth tables are manageable because it's 2 inputs, so it has 2 to the second power rows, right? But if you have a circuit that gets up to even 5 inputs, right, 5-bit inputs, that would be 32 rows. It's kind of gets a little unmanageable, right, the truth table. So truth tables are nice, but generally speaking, you're using them for classroom sort of toy problems, right? Not for anything really complex. So in this case, 3-input gate has 2 to the third, 8 rows. All right, so then we switched gears. We talked about logic levels. This is actually a timely topic because the voltage of modern chips is shrinking. And the reason for that is because the dynamic power consumption scales as voltage squared. So there's a pressure to keep shrinking the power supply voltage. But the question then becomes, well, if you're changing the voltage, then what is 0 and what is 1? How do you define your low and your high logic level? So the idea is that ideally you would have this sort of response curve where the horizontal axis represents the input voltage, and the vertical axis represents the output voltage if you have a very simple driver gate, that doesn't, this is assuming that whatever the input is, we're just going to set the output to be whatever the input is, right? So this is kind of like a buffer, basically, right? You guys with me? Obviously, if this was an inverter, this thing would be reversed, right? Okay, so the idea though is that if the input, once the input goes to half the voltage, right? So if it's a 5-volt system, once the input gets to 2.5 volts, then that should represent a transition between 0 and 1. In other words, this is assuming there's a simple threshold. You know, anything that goes over the halfway mark is a 1. Anything under the halfway mark is a 0, right? But actual circuits don't work that way. In fact, it looks closer to this, where as you increase the input, the output increases to a lesser degree, right? Until you reach a certain point, which is labeled VIL, which is it is the input threshold for low. That's what the L, I, input low. Once you get beyond that, the output voltage changes. It starts going up much faster until it then eventually levels out. At which point that's the V input high voltage, right? Once you hit the V input high voltage, the response becomes the output high. Sorry. So I kind of boofed that explanation. So the idea is that you have an input, so you can raise the input with very little effect on the output, right, is what I'm trying to say. Until you reach a certain point where the character, this, I think generally speaking, this is around 700 millivolts or so. We're on the threshold of the transistor, or around the threshold of the transistor, the N transistor. Then at that point, you're at VIL and you're at VOL, right? Output low, right? And then as you keep going up with your input, you'll eventually level out your output. So that'll become, you'll hit a point where your input voltage is VIL and your output voltage is VOL, right? At which point going above that as your input makes little difference in your output, right? So what that basically means is that this gate and all logic gates interpret the inputs in a kind of a forgiving way because they take whatever inputs are and they kind of fix them on their output, is what I'm trying to say. They condition the signals. They regenerate the signals, right? So you can have an input that is supposed to be a logic 0, but it's kind of like 300 millivolts because of some noise, right? Some noise got added, so we're not quite down at. I mean, we should be at ground. It's a 0. It's a logical 0. We want to be at ground ideally, but because of some noise was added to the transmission line, to the wire, we're really up at around 300 volts. But as it goes into this gate, the gate sees that 300 volts and says, well, you're below VIL, so my output is going to be, in this case, because it's an identity function, my output's going to be lower than 300 millivolts. The output might be 100 millivolts or 50 millivolts, right? So the gate fixed the signal, basically. It fixed it, right? It conditioned it. And that's what's happening here. So once you know where your VIL are and your VOL are, you end up with what's called a noise margin, which is the difference between those two. It's basically the difference, how far you can deviate, how far the input can deviate from what the output is for a low and a high, is your noise margin, right? So that's how much noise you can, essentially that's how much noise you can add to the wire without affecting the behavior of the circuit, without screwing up the bits in there. You guys with me? Make sense? So that's the idea. Now, now why are we talking about this? Well, because this seems like more of an electrical engineering type concept anyway, right? It's kind of an electronics thing. Well, it has implications for computer architects because as you lower VDD, you also reduce the noise margin, meaning that the circuits are more susceptible to noise, meaning that it becomes more likely that you're going to have an error. and not an error that not a repeatable error, like a random error. They call them transient errors or soft errors. Errors that just kind of randomly appear as a result of noise on the power supply or crosstalk. So, in other words, a gate can have a transient error because of activity of circuits nearby it on the chip, or radiation can cause this too. Believe it or not, cosmic rays, which most of them get blocked by the atmosphere, but some of them come through the atmosphere, and there's not enough to affect humans, but they can still hit this circuit and cause these transient errors. So, it's a problem. So how do you deal with that? Well, you have ECC. People say, well, why is the servers more expensive than a desktop computer? Well, one of the reasons is because they have more of this error correction codes built in to guard against errors, because they're supposed to have high reliability. There are lower standards for reliability for desktop computers than there are servers. You guys with me? And what is ECC? ECC are codes, like extra information you add to detect and recover from errors automatically. But that's outside the scope of 611. Okay, and then finally, sorry, I'm bloviating a little here. Silicon. So we talked about MOSFET devices. Let's see. MOSFET devices are kind of they look kind of like a sandwich. They're comprised of multiple layers. But the most important thing to understand is that the devices are 3 terminals. There's actually 4. There's a bulk terminal that's sort of implied. So the substrate, in this case, this is an NMOS transistor, also called an N-channel MOSFET. The substrate here would be grounded, and then you've got 2 diffusion areas that are your source and drain, and then there's a gate that controls the device. The gate is what basically, if you put in an N-channel MOSFET, if you put a 1 value, right, if you put something higher, high voltage level, logical 1 on this gate, it'll connect the source and drain together, right? And then a PMOS would be the opposite of that. A PMOS PMOS has an N substrate and P source and drain. Now you might say, wait a second, hold on. The substrate is the whole chip, right? The whole bottom of the chip. How is it that you can have a different substrate for N transistors than from P? It's because with PMOSs or PFETs, this part is actually called a well that's actually buried. So you have, it's kind of weird. You've got the whole chip is a P-type silicon. Then you have an island of N silicon in there, and then islands within an island, these 2 diffusion areas for the source and drain. You guys with me? So that's anyway. The turning on this device requires you to put a logical 0 here on the gate, right? Now you might say, well, wait a second, how does that work? I mean, why is it you ground it and it turns on? Well, not exactly. It turns out that what ends up happening is because this guy, this well is charged up to VDD, charged up to the power supply voltage. So when you take the gate and you put it to 0, right, you're putting 0 on here, but the gate is actually seeing negative VDD. If you look at the gate voltage relative to its substrate that's charged up, it's actually negative. So what's really happening with PMOS transistors is that they have a 700 millivolt threshold like the N do, but it's negative 700 millivolts. So you put a negative voltage above the threshold here to turn it on. You guys with me? Okay. All right, and the last thing, let's see, I think the last thing I covered last time, how do you build gates from transistors? When I first saw this used to confuse me endlessly, but there's a couple things you have to understand about this. One is that CMOS logic is negative Negative logic. So you can't make an AND gate or an OR gate. You can only make a NAND and a NOR. And the reason for that is because the NMOS transistors, which are the ones that turn on in response to a 1, right, are the ones that pull down the output to 0, to false. Right? Now, when I first saw that, I was like, then why not switch them? Why not put the NMOS up here at VDD and the PMOS down at ground? That would make sense, right? 1 would turn it on and 0s would turn it off. Makes sense to me. But it turns out that you can't do that because only PMOS transistors can pass a strong 1 and NMOSs pass a strong 0. And it has to do with the fact that the gate voltage is actually relative to the source terminal. So you need to have the NMOSs. Their gate voltage has to be relative to ground. So you have to put those on the ground side. And the PMOSs have a negative threshold that turns them on, so they have to be up here by VDD. That's kind of the simplified explanation of it, right? Makes sense? So what that means for you guys, though, in this class is that you have to understand that well, actually, the way it works is if I were to ask you to build a transistor schematic of an arbitrary gate, how would you do that? Well, you would think, well, I got to figure out under what conditions would it be true, right? Right? But no, you would have to actually think under what conditions would the output be false, and then build your NMOS network based on that, right? You guys with me? And then once you build your NMOSs, then you just build the PMOSs as whatever the reverse of these guys are. So in this case, because these guys are in series, these guys would then be in parallel. Make sense? At least that's how I do it. Maybe that's the way I've always done it, right? So if I give you a truth table and I say, all right, I've got A, and I got B, and I got out. Actually, maybe I should do, it's not going to work. Let me do a 3-input gate here. Yeah, A, B, C, 0, 1, 1, 1, 0, 0. 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, and then I have out. Let's see, I wonder if I can build, how's this going to work? So let's do an AND and OR, what is that, the AND OR invert gate looks like that. It's a typical gate that you can do in CMOS. So if this is A, B, and C, then whenever C is 1, the output, let's see, yeah, A and B, so if A, let's see, whenever A and B are both 1, 1, which would be these two, and C is, let's see, let me do it this way. Say A and B is going to be only, yeah, it's only these two guys, 1, 1, everything else is 0, right? And so then C, let's see, whenever C is a, whenever C is a 0, right, we want to put a 1, right? Yeah, so C is a 0, so that would be a 1, 0, 1, 0, 1, 0, 1, 0, 1, 2, 3, 4, right? 1, 0, right? Makes sense? So my output then is going to be it's going to be, so let's go, yeah, that would be 1, 0, 1, 0, 1, 0. So my output is going to be 1 under this case. So C would have to be 0, right?
The bottom two should be 0.
bottom two would be 0, right, because A and B, right. That's right. Because when A and B are both 1, then we'll put a 1 into one of this NOR gate. Whenever you have a 1 in a NOR gate, then your output's going to be 0, right. You guys with me? Make sense? All right, so now we want to build this in the transistor level. So we're going to pull down with the NMOSs, right? So we want to look at when the output is 0. When the output is 0, you got when B is 1, right? And when A is 1, right? So we're going to look at, let's see, all the cases where you have a 0 output is where you want to. So we can build a logical expression for that, right? So that would be, let's see, it would be C, not A, not B, C, right? And then not A, B, C, right? So that's this row, 0. This row is 0. And then A, not B, C, there we go. And then, yeah, as long as you've got A and B, right? And C would be a don't care. You guys remember that? Okay. So you would build. So you want to build your pull down network like that. So A and B would be, if you have A and B, if they're both 1, you have A and B, and then there would be ground right there, right? And this would be your output. Right? Or you can have, alternatively, you can have either one of these implicates here, these not A, not B, or C. So let's see, how do we minimize these? You're going to have, so the idea is that you have one option, so these are all combined with ORs here, right? So if you have A and B are both 1, then those would be on a parallel branch, and if they're both 1, they would both be turned on, and you'd pull down to 0. You guys with me? Now these two guys would be in parallel up on the pull-up network, right? All right. So then, let's see. On the other hand, if you've got not A, not B, let's see. If you've got these other guys, so you've got so if this is a Carnot map A, B, C, and we've got 0, 0, 1, 0, 0, 1, and then 0, 1, 1. 0, 1, 1, right? Make sure I don't screw this up. 0, 0, 1, right? 0, 0, 1, 0, 1, 1. Sorry. 0, 1, 1, right? 0, yeah, 0, 1, 1, right? And then the last one is 0, 1, 0. So that's 0, 1, 0, 1, right? So 1, 1, 0, and 1, right? So we got these two guys, which give us, this reduces down to not A and C, and then this guy goes like this on the Carnot map, and we've got not B and C, right? With me? So, so we want to have an OR, so we want to have not A there and C, right, in parallel, in series, and then not B and C. So, sorry, see that?
Can you close the screen?
Yeah. Wonder if I could lift it up without, yeah. Good idea. So not B and C. With me? Make sense? And that would be the pull down network, and this would be your output here. So the idea is that when you have AND terms, you have those in series, right? And OR terms would be in parallel inside the network. You guys with me? Okay. Now the pull-up network would be, instead of these guys being in parallel, you have them in series. And instead of these being in series, they'd be in parallel. So you'd have it like this. You'd have A. So you'd have these two guys, A, B, right? And then you'd go up like this. And you'd have not A, C, and then not B and C. That'd be your pull-up network, which would be complementary to the pull-down network. Make sense? There's an easier way to do that, but the idea is how do you translate the truth table into the series and parallel transistors. Okay. Generally speaking, though, you're not the gate library is a simple, they're simplified, and then if you wanted to do something like that truth table, you would just use multiple gates. You wouldn't build one complex gate. All right. Okay, I think in the power consumption, we talked about this. This is I think we actually got to this last time too. The dynamic power consumption is 1/2 times the capacitance, voltage squared, and frequency. So the capacitance is something generally that you would have to get from the design, the layout, the polygons. And it's going to be, the capacitance is just essentially how much metal you're driving, how much metal you're trying to charge. So it's the surface area of the gates, which serve as the inputs for the gates of the transistors, which serve as the inputs to the logic gates, as well as all the wires that you've got, right? The VDD is, VDD squared, the power supply voltage, and the frequency is the frequency at which you're switching, right? So this is why processors use try to shut off parts of the chip that they're not using. One way to do that is to just gate their clock. So you turn the clock off to certain modules, and then you reduce this F term, right? Or if you turn down the power supply voltage, you're affecting the V term. And the capacitance is the surface area, right? So if you make the transistors smaller, then that gives you less surface area, right? Less surface area on the gates. It doesn't affect necessarily the wires, although if the gates are smaller, you can put them closer together and you can get smaller wires. Everyone make sense? Yes?
Why is the VDD squared?
Good question. I forget about. It's because it's the energy required to charge a capacitance. Yeah, it's the capacitor. It's how much energy to charge a capacitor is the capacitance times VDD squared, right? This is, I guess I forget. I guess it's in joules. Yeah, because then if you have joules, that's right. If you have joules and then you multiply that by frequency, that's going to make it converted into power, right? In other words, this represents the energy to charge a capacitor, right? And then this is how many times per second you're doing it, right? So it's energy per second. Chart, joules per second. It's going to give you watts. All right, static power consumption is the, in the old days, it wasn't a very significant amount of power because CMOS gates have high, when you turn off a CMOS gate, it has high impedance, right? But the problem is that we're lowering the voltage and we're getting closer to the threshold. And so the effective impedance of the CMOS transistors is less than it once was because we're lowering that VDD. So the static power, the static is not a function of frequency, and it's this is kind of a cop out, but they have this term IDD, which is the leakage current. So this is the total leakage current that is leaking. In this case, like you have a gate design like the one we did up here. Even if you have one side turned off, right? You may have the PMOSs turned off, right? And the NMOSs are turned on. But what does it mean to be turned off? Does it completely disconnect them? No, there's still there's still some leakage that comes from VDD down through these transistors, and then of course they go through these transistors because they're turned on, right? So the leakage goes down through the pull-up network. In this case, if I'm pulling down, we get leakage through the pull-up network, and then once it gets here, it's going to of course leak down into ground, right? But and that's what this leakage current is, IDD. You guys with me? And this is power that's just constant. It has nothing to do with clock gating, doesn't affect it. Alrighty, I had an example there, but I'm going to move on because I'm way behind where I wanted to be. Okay, chapter 2 focuses on logic. Most of this chapter is also kind of review from 211. So I'm going to go through this kind of fast, but let me know if you have a question or if something's not clear. So logic circuit is comprised of inputs and outputs, something inside there which includes a functional specification, what it's supposed to do. I mentioned earlier, this could be like a truth table or a Boolean expression, and the timing spec, which is the timing, how long it takes to get signals, how long it takes for the outputs to change with respect in response to the inputs changing. If you drill down, you've got elements inside there. If there's elements which represent like gates or other modules, and there's intermediate signals. There's internal signals. So when you write code in an HDL like Verilog, this would be called a module in Verilog, and you would have these top-level inputs and outputs of the module that kind of look like, if you're in Java, you're using an object-oriented programming language, these are sort of like the interface method, sort of. It's the way that the outside world interacts with this module. Sort of the public-facing interface, right? The top-level inputs and outputs. And then but you can still have internal signals in there, which are kind of like private members, right? Intermediate signals, internal signals that are not exposed to the outside world. Make sense? If all the elements inside there are gates, like they don't have any memory, then it will be a combinational logic circuit, meaning that the outputs are the output of the circuit is determined only by the inputs. The output is a function of the inputs, right? So in this equates directly to like a truth table or a Boolean algebra expression, right? It's combinational. Some people call it combinatorial. It's really combinational logic. On the other hand, if you have any memory inside there, any kind of elements that retain value, then it's a sequential logic circuit, in which case the outputs are determined not only by the inputs, but by the input history, or the history of inputs, the past. Okay? You guys remember that, right? Did you cover? I don't think they cover sequential logic in 211. So the next chapter is on sequential logic in this course. We're going to focus on combinational logic in this chapter 2. Okay. Now, it's also one of the weird things about combinational logic, though, is that even if you have only logic gates inside of a logic circuit, it's assumed that there's no cyclic paths, that none of the outputs of any of those gates feed back to inputs that could possibly affect that output. Make sense? If you do that, you could inadvertently create sequential logic by having these cycles, right? The problem is that making sequential logic elements like flip-flops is actually pretty tricky, because it's hard to make circuits like that are stable. And so in general, if you have any cycles inside your logic gates, it means you messed up. There's a bug. It's usually unintentional, right? You guys with me? Okay. So here's an example. This is a very classic example. This is a full adder. There's 3 inputs, A, B, carry in, 1 output, or 2 outputs, sum and carry out. So basically, it's like saying I want to add 3 1-bit values and produce a 2-bit output. Does that make sense? So if I put 1, 1, and 1, it's 3, and I can represent 3 in 2 bits. So that would be the output would be 1, 1, right? So in other words, a full adder is taking 3 inputs that are treated each as 3 separate 1-bit values that I want to sum together into an output that is a 2-bit output. You guys with me? Okay. So you can build. Now, in this case, I've got 2 outputs. So I've got 2 separate expressions, one for each output. The sum is A XOR B XOR C. So it's like a 3-input XOR gate, meaning that if there's an odd number of 1 bits coming in, then my sum will be 1. So if I have 1, if any one of these is 1 and the other 2 are 0, then I'll have a 1 on S. And if all 3 are 1s, then I'll have a 1. And then C out says that if I have at least 2 1 bits coming in, then I'll have a 1 in my C out. You guys with me? Okay. Okay, so there's some definitions. If you have a variable with a bar, it's a complement. But this notation is really weird. If you look, other places do this differently. You guys might have seen, like, sometimes they'll do one of these numbers where they'll have a little, like, sideways L. Right? And that's a complement. You complement A. Right? Sometimes they do it like they have a tilde A. That's actually how you do it in Verilog. Tilde. How else is it? Is there any other ways? I like the bar. The book uses the bar notation. So this is not A. Literal is any variable or its complement. So when I did this circuit diagram, I used literals when I plugged these inputs into the gates, because some of these were complemented. Implicate is a product of literals. The midterm is if you have an implicate that includes all input variables. And I often will switch. I get these confused, implicate versus midterm. It's not a huge difference, but implicate is just more of a general term, whereas a midterm is when you have all the literals in there. And max term is the sum of all the input variables. Product of some form is where you have, if you build your expression in a form called sum of products form, it means that you define the behavior of your logic as a sum of min-terms, right? You guys with me? Sum of products, right? Now, what is the significance of that? Who cares? Well, the significance is you can define any Boolean logic function in this form, right? But there's a couple problems with it in practice. One of the problems is that if you're using sum of products, there's kind of an assumption that there's no limit on the number. Like, well, let me first say this. If you're using sum of products and your plan is to put that in hardware, right, to synthesize that in hardware, there's this assumption that you have sort of an unlimited ability to create gates, right, in terms of the number of inputs. So in this case, I have 2 inputs and 1 output. And so I can build the sum of products by looking at the rows where my output is 1. And then I can build my min-term by looking at the values that produce that 1. So because A is 0 and B is 1, it's not A and B, not A and B. And if in this case it's A and B, right? So I've got two min-terms there. So in that, how would I build that in logic? Well, I would need to have 2 AND gates with 2 inputs, right, to have those 2 min-terms. But then I would have to have 1 2-input OR gate, right, to add them together, right, to sum them together. Sum together. And when I say sum, I mean or together, right? You guys. Now, that's not a big deal, right? Because, yeah, you're always going to have 2-input AND gates. But when you scale this up, do I have a bigger example? I don't have a bigger example. But as you might imagine, if you have a bigger table, your min-terms are going to need to have AND gates that can support the number of variables, right? So if I have 3 inputs or 4 inputs, I might have to have a 4 input. But what's more problematic is that I'm going to have an OR gate that sums all the min-terms. That's going to have a number of inputs as defined by the number of min-terms, or the number of ones in my output column. You guys with me? And the problem is that generally speaking, you're not going to have that. You're going to be limited in your gate library. Most of the times you can have 2 input gates and 3 input gates. Sometimes you can have 4 input gates, but never any more than that. So we'll talk about how you deal with that in a minute here. This is just an example of how you can build. I guess, now what's the idea here? I guess we have a description of the behavior, and we want to build a truth table. So you won't eat lunch, meaning that your output will be 0, right? It'll be complemented. If the cafeteria is not open, so that would mean any row where O is 0, or if they only serve corn dogs, if C is 1. So the idea is that we want to put zeros here in the output column for every row where O is 0, right? So that would be the first 2 rows, right? 0, 0, right? Or if C is 1, which would be the last row, right? So the output here should be 0, 0, and then a 1, and then a 0, right? Yeah. OK, so this is the same thing. We've got min-terms. Max terms are it's very similar to min-terms. The difference is instead of products, each max term has all of the inputs, literals for all the inputs, and combined with sum, with OR, and then you AND them all together. But the thing is that there's this additional detail with max terms in that the max terms, each of the literals is inverted with respect to the input. So notice the max term is O plus C. O and C are not complemented. I say inverted, but if I say inverted, I mean complemented, right? Inverted, complemented, it's the same thing. O and C are not complemented, right? But yet they are zeros here, right? Make sense? The reason for that is because of De Morgan's law, and I'll get to that in a minute. But just keep in mind that when you build max terms for each row that correspond to each row, you invert each of the individual variables with respect to their inputs in the truth table. You guys with me? Make sense? Okay. Okay. So whenever you build your, so in this case we're starting with the truth table. I want to get a Boolean expression. I want to put it in sum of products form. I pick the rows where I have a 1, and then I grab the corresponding min terms, right? Make sense? Max terms are kind of the opposite. I look for rows that are 0, and I grab their corresponding max terms, and I build my product of sums form. You guys remember this from, did you cover this in 211? Okay. Okay, what would be the advantage of one or the other, by the way? Why would I go one way versus the other? Well, these are equivalent. This expression, this Boolean expression, and this Boolean expression are equivalent in the sense that they both give you the same truth tables, and they are both true under the same conditions. They're both false under the same conditions, right? So it's redundant, right? Why have two ways to do it? It's the same thing. Yeah, this is pretty rare. Most people don't use product of sums. But you can imagine, though, that there's a difference in the hardware requirement, right? So if I'm trying to implement this in hardware, one of these approaches is going to require more hardware than the other, right? This is one gate. This one is, well, how many gates is this? You have to count the number of operators, right? So there's 1, 2, 3 ORs and 1, 2. Well, there's 2 OR gates and I'm sorry. There's 1, 2, 3 OR gates, and there's 1 AND gate that takes the output of all the ORs. But that's counting in terms of gates. If you count in terms of inputs to gates, then it would be 2 inputs, 2 inputs, 2 inputs for the so 6 total inputs for my OR gates, and then 3 for my my OR gate, my AND gate. Sorry, there. You guys with me? Okay. All right. And this is also the reason why you would want to simplify a Boolean logic behavior before you implement it in hardware, because you'd be using less resources, right? So, you can do that with the Carnot map as I did over there earlier, or you can use you can do it algebraically using Boolean axioms and theorems. What's the difference between an axiom and a theorem? Anyone know? Theorems can be proven with axioms, right? But axioms are just kind of statements of fact, can't be proven, right? It's kind of like a hierarchy. Axioms are at the bottom of the hierarchy, and then using axioms we build up into theorems. So a lot of these are kind of common sense. So let's see, the identity theorem. If you have a variable and you AND it with 1, you get whatever the original variable value was. If you OR it with 0, it's the same thing. So, gate-wise, it's like hard coding an input to a gate, right? The null element theorem is kind of the similar idea. If you AND anything with 0, you get 0, and if you OR anything with 1, you get 1, right? Then you've got the idempotency theorem. And this is kind of, if you AND something with itself, you get that value. And if you OR something with itself, you get that value, right? So it's kind of like having the same value going to both inputs on a gate. If you double invert or double complement something, you get the same thing. That's the identity theorem. It's like having 2 inverters in series, and of course complement. If you take a value and you AND it with its complement, you're guaranteed to get a 0, and if you OR it with its complement, you're guaranteed to get a 1. All right, and this is a summary. Summary of those The double complement is called involution. That's not what it says there. It says identity. I think that's a typo in the book's lecture slides. The involution. Involution. Okay, then you've got the ones that are more interesting. These are the theorems of when you have several variables. So now a lot of these things follow the same rules you have in algebra, right? So commutativity, I always remember that because it starts with CO, and CO, I think of that as change order, CO, where you can take the order doesn't matter for ands and ors operations. Associativity is when you, if you have three input variables and you want to OR them all together, for instance, it doesn't matter what order you do them in. You can have a two-input. In other words, basically it allows you to take, instead of a three-input OR gate, you can have two-input gates that are cascaded, right? Likewise with AND. Distributivity, same thing as in algebra. This one, though, is a little weird because notice this one you've got, this one's a little hard to remember, B or C and B or D. The B is a common element there, so you can distribute the B over OR over the C and D. This one is a little different, but it's unique to Boolean algebra. Covering is in this case now each one of these has a dual, by the way. It's when sort of the AND version and the OR version. But in this case, B or B and C is just equivalent to B. Because, why is that? Well, if B is true, then, you're going to get true, right? Because true ORed with I don't care is true, right? But if B is false, then you're going to be ANDing C with false, which is guaranteed to be false, and B is also false, which is an OR, so you're going to get false in that case too, right? Make sense? So it's kind of hard. I always have trouble remembering all these, though. Combining was when you take, this one's kind of makes sense. If you have C and you OR it with B, and you have the complemented C and you OR it with B, then that's just equivalent to B. This is the one that I really, really can't, and I've never been able to get my mind around this one, consensus. So follow this one for me. The way I've always thought of this one kind of like I've done a Venn diagram for this one. If you have A, B, and C, right? And what you're saying here with consensus is you're looking for B and C, so that would be where B and C overlap, right? Which would be this area, right? B and C. Or we're going to add to that not B and D. So, this one's B. I'm sorry, this is B, C, and D. And there's no A. Sorry. Relabel those. B, C, and D. All right. Sorry. So we've got B and C, right? So this is this area now. Right? Not B and D. So this is the area here that is kind of D but not B, right? Make sense? And C and D, right? All right, which is already included there, right? So that is equivalent to just saying B and C, right? B and C, which is this overlap area, right? So that would cover this part. And not B and D, which is this part, right? So it's consistent, right? That makes sense? Now, it makes sense doing it that way. Looking at it, it's confusing. It doesn't seem to make any sense just looking at it. All right, and then De Morgan's theorem is when you have, if you have an implicate here where you've got literals that are ANDed, if you complement that whole expression, then you change the ands to ors and you invert each individual literal, or complement each individual literal. You guys with me? Or variable in there. All right. So these are some examples of you can use these to simplify logic. So in this case, if I've got this expression, now just looking at that, it looks fine to me, right? But it's more complicated than it needs to be because you can take B out through distributivity, right? Just like you would in algebra. So B and with A or not A, and then A or not A. Well, that's redundant, right? That's just true. So that just becomes a 1 or a true, right? And then if you AND something with 1, it's just the original value. So this is just equivalent to just B, right? In this case, you can take, you got this expression. You can take A and B out through distributivity again. So this gives you A and B, and then ANDed with true or C, which is just equivalent to true. So this kind of drops out. And then A, obviously the 1 drops out when you AND it with A and B. It's just A and B. And then in this case, you use associativity to move the parentheses around A, and A is equivalent to A. So this whole thing reduces down to A and B. You guys see that? Okay. All right. Let's see, how much time do we have here? Okay, it looks like I'm about up. I have a really nice another example of this. So which I'm not going to get to. I'll get to it on Monday. But the interesting thing about these rules is that you can use them to simplify logic, but you can also use them to change. I mentioned the sum of products. I mentioned that if you do sum of products form, you may end up with a simplified expression, but you may not be able to implement it directly in your logic because you may not have gates with enough inputs to directly map your sum of products form onto the hardware. You guys with me? This is a mapping problem. So it turns out that it is more common in CAD tools to use these rules not necessarily to minimize the number of gates, but to limit the number of inputs on an individual gate. And also, you can use these rules to do things like reduce the critical path of your circuit, which changes its timing spec. Or you can use it to balance a circuit. You can balance the paths of the circuit if you want to try to eliminate glitches. You guys with me? So the idea is these rules allow you to transform a Boolean expression into an equivalent form that gives the same truth table and has the same behavior, but it changes the hardware needed to implement it. So as a result, these rules and doing this stuff is actually more important than you might have thought when you first saw this in 211. And I have a pretty neat example of that I'm going to show on Monday. Okay, so I'll see you then. Have a good weekend.